In the previous videos, we've been looking at the distribution of sampling error. And remember what this is. This is the distribution of how much error we experience between the population parameter and the sample statistics we actually observe. And what we saw is that sampling error, under some conditions, has a normal distribution. Now, that will be very convenient for us if the distribution of sampling error is normal, because we know a lot about the proportionality of the normal distribution. But we need to investigate further what are the conditions under which we can expect the distribution of sampling error to actually be normally distributed. In the rest of this module and the modules to come, we're going to look at two interrelated topics: the distribution of sample means, what we've been developing right now, and the logic of hypothesis testing. These two topics are intimately related. The distribution of sample means underlies the logic of hypothesis testing. In fact, the logic of hypothesis testing is really just a formalization of using the distribution of sample means to make inferences from a single sample we take to the population parameters we're actually interested in. And remember, in real science, we're never taking these repeated samples. We're never forming a distribution of sample means. Instead, we take a single sample, and using that sample, we're trying to make inferences about the population. The reason we're looking at the distribution of sample means is so that we can understand why the logic of hypothesis testing works. That is, how is it that we can gain insight to a population we don't know about on the basis of a sample that we have observed? As we'll see, the key to this puzzle is understanding the distribution of sample means, specifically knowing its characteristics, its mean, and its standard deviation. Now, before we get into that, let's pause and talk about the types of designs we're going to be able to use the distribution of sample means for. First, and what we're going to spend time on today, is talking about single sample designs. Now, single sample designs are really part of single group experiments, and single group experiments have corresponding analyses. What we'll see is for a single sample design, we can use things called a t-test and a z-test, something we'll come back to. We can also talk about pre-post designs, where we measured somebody once, treated them in some way, and then measured them again. That's also going to use a t-test, which fundamentally is based off of, again, the sampling distribution of the mean. We can also do designs in which we have multiple groups. So a two-group design, where we take two separate samples, treat them differently, and then make an inference about why the groups differ. That will also turn out to be a form of t-test. We can also have continuous predictor designs. For instance, suppose we, instead of giving somebody a drug or not, instead give them some level of drug, so 5, 10, 15, or 20 milligrams. This will use something called regression analysis. If we have multi-group designs more than two, we're going to learn how to analyze those using something called the analysis of variance. These still require the use of sampling distributions at the root, although the formalization of these models may look a little bit different. Going back to the single group experiments, we can imagine a situation where instead of measuring somebody twice, that is, in a pre and post design, we form repeated measurements on those individuals. Those are called repeated measures designs, and we'll analyze those in this course using something called a mixed effect model. At the bottom, we can think of mixes of these different types of experiments. A situation where we have a group design, potentially males and females, that we measure repeatedly. So these are individuals who belong to different groups, but we've measured in multiple times. These will also use a mixed effects model. Finally, we can think of another mixture, a situation where we have groupings, but we've also measured these individuals on some kind of continuous variable. That will use something called an analysis of covariance, a variant of the analysis of variance we'll spend a lot of time talking about. Now for now, let's go back to the simplest design we can think of, a single sample design. And this is a situation like I described before. For instance, we have a population that we know a lot about, the IQ scores of all individuals in the United States. Now what's nice about the IQ distribution is that it has a mean and standard deviation we know. And we know this because this is a property of that test. The mean on many IQ tests is at 100, and it has a standard deviation of 15. Suppose we were interested in the effect of a nootropic, a drug that's purported to actually affect intelligence. Suppose we take some individuals from this population, again a population we know a lot about, and we treat them with a nootropic like ginseng. Suppose we give them ginseng for 6 months, and then we measure each individual's IQ in our sample. Suppose we have 16 people in our sample, and here are their IQ scores. After we've measured them, we would take an average. The average in our sample is 106. We also get a sample standard deviation of 15.2. Now, probably the most straightforward thing to look at here is how does our sample mean compare to the population mean? That is, does our sample mean reflect that population? Well, of course it's different. 106 is a different number than 100, but let's not jump to making an interpretation about the effect of ginseng just yet. Remember, in science, we have 2 explanations that we can use. The first is that there is no effect of ginseng on IQ, and that 6-point increase is due just to sampling error. We'll call that an epsilon-only explanation. That's the explanation that says just sampling error was occurring here. Us giving these individuals ginseng actually did nothing to their scores. Now, certainly, that's possible. We know that's possible. We know sampling error is always something we have to deal with. But we don't yet know how likely it would be if there was no effect of ginseng that we could observe a 6-point increase. It could be like getting a mean of 1 if we had 100 coin flips. That would be incredibly unlikely. Or it could be like getting a mean of 0.52 if we had 100 coin flips, which would be very likely. We need to know how unlikely that first explanation is when there's no effect of ginseng in order to say anything conclusive. But at this point, realize that we can't claim the second explanation is a good explanation until we can eliminate or at least discredit the first explanation as being reasonable. We'll come back to that logic when we talk about the formal logic of hypothesis testing, but at this point, notice that if we can discredit the first explanation, that is, we can say it's an unreasonable or unsatisfactory explanation of the result, then we're allowed to claim the second explanation is reasonable. That is, once we can eliminate the chance explanation, we can start to interpret this effect as having some real signal. Notice, in the second explanation, we're still measuring error. Sampling error will always be with us. But in the second explanation, we're assuming that there's one additional entity, a tau, some treatment effect that actually has a true effect in the population. And it's going to be that distribution of sampling error, the thing we've already observed, that's going to give us the inferential powers, the key to knowing whether that first explanation is reasonable. And the way we're going to do it, just to foreshadow a little bit, is we'll define regions of our distribution of sampling error, the one that we know exists if we were to simply be taking samples. We'll define some regions that are very unlikely when we're simply taking samples from a population. That is, we don't expect to get very extreme amounts of sampling error. When we're flipping coins 100 times, we don't expect, if we simply add up the number of heads, that we'll get all heads. That would be an extreme amount of sampling error. Similarly, getting no heads if we flipped 100 coins would be an extreme amount of sampling error. So there are regions where we don't expect an extreme amount of sampling error. And what we're going to do, the whole purpose of hypothesis testing, is to figure out, is the observed amount of difference that we found, in this case a 6-point difference, is it a reasonable amount of sampling error, something that's fairly central, an amount of sampling error that would typically happen, or is it a very unlikely amount of sampling error, the kind of sampling error we wouldn't observe very often? Now notice, I can reframe this distribution of sampling error to be a distribution of sample means. Notice the only thing I changed is that the center now is at 100, that is the population mean of IQ, and 106 is where 6 was before. 6 points of sampling error like I had before is up there in the tail. But again, we don't know if 106 in a distribution of sample means is one of the extreme ones or one of the fairly typical ones. That's what we need to figure out. And that's where we turn our attention to now.